We now learn an important test to determine whether an infinite series converges. That's called the ratio test. Let's look at a general infinite series. So I'll start from n equals 0 and go to infinity of a sub n. So this one is equal to a naught plus a1 plus a2, etc. And I want to compare this series to the geometric series. So remember, the geometric series was the sum from n equals 0 to infinity of x raised to the nth power. So that was equal to 1 plus x squared, etc. Okay. The reason I'm comparing a general series to the geometric series is because we know the convergence properties of the geometric series. We know that if x, so the geometric series converges, only if the absolute value of x is smaller than 1. Okay? The property of the geometric series is that the ratio of consecutive terms is equal to x. So as the series goes out to infinity, the only thing that's going to be important for our general series is what is the value of the ratio of consecutive terms. We expect that to converge to some number. So it's the n terms of the series that's important. And if the ratio of the consecutive terms is less than 1 in absolute value, then we can compare to the geometric series and say that this general series will also converge. So that's called the ratio test. So the ratio test says that if the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n equals L, then we get the result that the series converges if L is smaller than 1. It diverges if L is greater than 1. Okay, so that's by looking at the comparison to the geometric series. The case equals 1 is actually special. So you can come up with different series where it converges when the ratio is 1, or it diverges when the ratio is 1. This is like the harmonic series and the alternating harmonic series. So it's indeterminate if L is exactly equal to 1. So those are the boundary cases. Okay, so that's called the ratio test. So to determine if a series converges, you take the ratio of consecutive terms. You should look at the absolute value and then take the limit as n goes to infinity. If the ratio is less than 1, then it converges. If it's greater than 1, then it diverges. Let's look at an example. This turns out to be a very important example. Let's look at the sum from n equals 0 to infinity of 1 divided by n factorial. So what is this? The first term is 1 over 0 factorial. We define 0 factorial to be 1, so the leading term is 1. The next term is 1 over 1 factorial, which is just 1. The next term would be 1 over 2 factorial. 2 factorial is 2, plus 1 over 3 factorial. 3 factorial is 3 times 2 is 6, plus 1 over 4 factorial, which is 24, etc. Okay, so the denominator is growing very rapidly here. Does this converge? we can look at the ratio test. So we can look at the limit as n goes to infinity of the n plus 1 term, right, divided by the n term. So the n plus 1 term would be 1 over n plus 1 factorial divided by the nth term, which would be 1 over n factorial. Right, we can fix the order here. So this is the limit as n goes to infinity. The n factorial is in the numerator. The n plus 1 factorial is in the denominator. All the terms cancel except one term at n plus 1 in the denominator. So that's the limit as n goes to infinity of 1 over n plus 1. And then the denominator goes to infinity, so this is just 0. 0 is less than 1, so that this series converges. We would expect this series to converge because the denominator is growing rapidly. But what we might not expect is what the value is. So the value of this series, which we will compute later in this course, turns out to be the Euler number E, one of the miracles of calculus. So let me summarize. I'm teaching you now the most important test to determine whether a series converges. That's called the ratio test. What you need to do is look at the ratio of two consecutive terms in the series as the n goes to infinity, way out, and calculate that ratio. What does it converge to? It converges to L. It could be infinite, but let's just call it L for here. So if L is less than 1, the original series converges. If L is greater than 1, including infinity, the original series diverges. And then we have this pesky boundary case, L equals 1, where the ratio test actually fails, and you can't tell whether the series converges or diverges. I'm Jeff Chasnov. Thanks for watching, and I'll see you in the next video.